begin the lesson section. Challenge, please.
Known as challenges number 8, potential lines.
What number?
Number 8.
Number 8.
We accept the challenge.
Accept number 8. Please write down your full name on blackboard.
I'll start my presentation. Good morning, fellow students, fellow competitors and judges. I'm Jonathan Pong from Team Laplacian, and today I'll be presenting number 8, equipotential lines. Here's the problem statement. So place 2 electrodes into water, supply a safe voltage, and use a voltmeter to determine electric potential at various locations. investigate how the measured equipotential lines deviate from your expectations for different conditions in liquids. So in our view, there are three key questions to consider. First, what does the voltmeter measure in a solution? What parameters affect the potential in a solution? And how do these parameters affect electric potential? And here's an overview of our presentation. So before we jump into the main question, we first have to figure out how a voltmeter works in a solution. So voltmeter measures the tendency for ions in the solution to migrate or to move along the electric field lines. And it doesn't matter whether the voltmeter measures the electrical or the chemical forces. Also note that the current required is so small compared to the total amount of charged ions in the fluid. For our experiment, we have three types of setups to measure different parameters, and this is our first experimental setup. Here we have two electrodes positioned at two ends of the tank, and we also have 6 detecting electrodes lined up in a line at the center of the tank. The device we use to measure the voltage is an Arduino Uno board and also a variable resistor. And there are 7 notches positioned along the tank here, and we can use these notches to collect a total of 42 data points for our measurements. And for method 2, we measure the time-dependent variation of the voltage distribution in the solution. And the 6 electrode detectors are positioned according to a diagram there. Our final setup is used to measure voltage that's beyond the capacity of our Arduino board. To do this, we connect the system to an external power supply to give the voltage we need, and we measure the voltage using a multimeter. And also the parameters are given here below for our various experiments. So after experimental setup, we've come to the observation we made. And using experiment setup 1, we can measure the spatial distribution of the voltage in the tank. And we use Python and matplotlib to plot the various distribution of the voltage inside the tank using a contour plot. And there's a total of 42 data points using 3 sweeps of the detectors, as mentioned below. So we have a total of 42 data points for our contour plot. So here's our expectation of what might happen. Assuming that the voltages are symmetrical with respect to the center line here, we should expect that the voltage measured at the center of the tank is actually half of what is supplied. And also, the equipotential lines given by the 2 electrodes should be like that of 2 charges in a plane. And this happens to be Apollonian circles with the radius of one of the circles, which is this one and this one. And this happens to be the voltage of the electrode surface. So we can model our expected voltage distribution using the Apollonian circle model. And for our experimental observation, we noticed 2 main deviations from what we said. First, the voltage. Our first observation, the voltages actually drop drastically near the 2 electrodes when compared to what we might expect using the previous theory. And second, the voltage drop at the anode is actually higher than at the cathode. So we find that also at the center of the tank, it's significantly lower than what we might expect to be the half of the supply voltage. And also it's not symmetrical. So our second observation using experimental setup 2 is this. The voltages are measured as a function of time in seconds, and the y-axis is the measured voltage. And here is the pin 5, which is closer to the cathode, and pin 0, which is closer to the anode. So we find that the temperature effects, these three lines are set respectively at 5.6 degrees and all the way to 56.8 degrees. So we find that the temperature actually affects the rate at which the voltage reaches equilibrium, and higher temperature means less voltage change and faster rate to reach the equilibrium. And also that, judging by this, we can go back to our previous observation that the voltage drop at the anode is actually higher than at the cathode. The above are our main observations, and now we will try to explain and justify our observation using a theory of electric double layers. It was first proposed by Helmholtz in 1879, and what the model says is that outside the electrode in a solution, a thin layer of charged particles or ions can accumulate on the surface of the electrode, and thus shielding part of the effect of the electrode. And this effect will decrease the voltage that we can measure using our voltage detectors. Also, there's according to diagram B, there's a diffuse layer of opposite charged particles, and these diffuse layer will make the voltage distribution deviate from what we expect from the classical theory of electron theory. From this diagram is the electric double layer theory given by the Stern model, and we can see that just near outside the electrode there's a diffuse layer and then a bulk layer, and what's shielding the voltage is the thin layer of charged particles. This can be described by the Boltzmann distribution, and when we solve for the Poisson equation according to electrodynamics theories, we can find the Poisson-Boltzmann equation as follows. And we'll discuss this equation in the next slide. Solving for the gradient of the voltage, which we can measure, we can find this relation to a temperature T, to the ion concentration, and to the voltage measured phi. We know that here kappa to a -1 can represent a diffuse layer. We can find a few things from this theory, that when applied voltage and temperature, when applied voltage or ion concentration increase, the gradient of the voltage also increases, and when temperature increases, the gradient of the voltage actually decreases. So a problem statement asks us to find a deviation from our expected theory. So our hypothesis is the following. First, there's a threshold voltage, and when the applied voltage is below the threshold voltage Vt, we cannot measure any voltage at all. Here's a graph of the various threshold voltage measured and at pin 5 and at pin 0 for various voltages supplied. And the experimental conditions are the same as before. And this is a graph explaining the effect of the EDL on the reference electrode and also on our voltage supply electrode. And after this, we consider the effect of ions in the concentration using 75% ethanol solution. And we find that the deviation is actually very close to what we expect using our previous theory without the EDL. So this is a graph of the ethanol to time deviation, and also when we adding NaCl ions into the same solution. And so we find that increasing the ion concentration actually raises the EDL effect very significantly, and also that the ion concentration effect on the metal electron interface and the bulk solution is also visible in our plot. And according to our theory, we predict that there's a threshold voltage, but the threshold voltage cannot shield all the voltage. As in real life, we can always observe some sort of voltage given by the supplied electron. And this is a plot that illustrates our prediction for the effect of the measured voltage and the applied voltage. And here, the small x-intercept is the small voltage shielded by the EDL, and also that this relation is not necessarily linear. So the ion concentration also increases the EDL effect as mentioned before. Now for our summary, the electric double layer is the main cause of the deviation from our expectation, and also that it develops on a scale of just seconds, which is very fast. Also there exists threshold voltage, and when we apply voltage below that, no voltage can be measured. And this voltage increases with ion concentration. Also that all pins experience EDL, and higher temperature means faster EDL formation. And that's the end of my report.
Okay, Mr. Reporter, thank you for a wonderful presentation, but I've got a few questions for you. So first, did you consider boundary conditions like Newman or Dirichlet boundary conditions?
No, in our theory.
Okay, thank you. Did you consider depletion and accumulation of the anodes and cathodes?
I believe we do not consider the depletion of the ions.
Did you ignore it seems like you ignored the Z direction equipotential lines?
Yes, we are doing the contour plot for the horizontal distribution of
okay, we'll talk about that later. You don't seem to have any error bars in the graphs.
Yes.
No, I don't see any error bars. Okay. You identified voltage drops by certain points. Did you consider moving your voltmeter, one of your voltmeter points across your solution to test this?
Yes. We have various different measuring points as illustrated in this diagram.
Okay, so you have 6 points that are now being changed, so you aren't measuring. You can't measure, for instance, points in the middle. All right. So next question: did you consider using hyperbolic functions to model your sound Boltzmann distribution?
Although we mentioned the hyperbolic distribution in our theory, in practice we don't think that's a good way to model this phenomenon according to.
Okay, we'll talk about that later. Did you consider a specific time of measurement where it is most stable and that there will be less confounding variables and classifications?
Not in this report, no.
Okay, thank you. That concludes my questions.
component, please.
Yes. This is the right equipotential lines. I'm not sure junior from known items. The problem statement is here. You can read it by yourself. We'll structure our investigation. First, the ions movement and the chemical reaction influence overall formation. We'll talk about the theoretical model, experimental analysis, and limitations to improve your model. So here are the pros and cons for the reporter's report. First, he had multiple effective setups. He had analysis between theoretical and empirical conditions. He considered some crucial parameters that would vary the overall shape of the formation, even though I will add that he's missing half of the entire presentation overall by not including boundary conditions. He has some reasoning behind the theory that's relatively clear, and he also included the electric double layer effect and the Boltzmann Poisson distribution. The cons for the report were that he didn't consider boundary conditions. That's really, really bad. Unfortunately, he didn't consider specific redox reactions that lead to accumulation and depletion on the anodes and the cathodes. You didn't identify any error analysis or perform any error analysis at all, nor did you consider using hyperbolic sign functions, but I don't think you identified the fact that the computational errors of computers cannot handle such things without simplification. And there is, again, no best fit line and error bars and graphs. So here will be our points of discussion. First, we'll talk about multiple points. First, we'll talk about our experimental setup. We'll discuss your plotting and experimental methods, and I would like to, again, verify that I use fixed points of measurement, which I think do not contribute too much to the quality of the graphs. Topic 2 will first briefly cover the z direction of equipotential lines, why you omitted that. We'll talk about boundary conditions. We'll talk about Stern layers, which you kindly mentioned, and the possibility of using hyperbolic functions. And then we'll move on to your experimental work. I would like to discuss the possibility of there being a specific time of measurement where there are no confounding variables. And again, computational problems, and due to hyperbolic function lack and depletion and accumulation that results as a result of the cathode being having anions approaching it and vice versa. So we can start our discussion. So first, I would like you please to go to experimental approach. So where you had the 16 dots, or yeah, this one. So from what I understand from our 32-minute interview, you have these fixed points that you're measuring from.
Yes.
So it's impossible for you to measure, say, this point.
No.
Have you considered fixing, and you have a voltmeter, right? It measures the voltage difference between 2 points. So have you considered fixing a voltmeter, say, on the left side, and then moving around the right voltmeter at different points to test the voltage?
If not, it's going to give too much of an error if we try to move the whole setup for each of the measurements. So that's why we consider fixed points as shown in the picture.
I agree that there will be error if you move both of them, but I'm saying you fix one of them and you move the voltmeter. Say you stop here for like a minute and measure it, and then you put it here and measure it, and then you put it here and then you measure it. Because the problem, usually I think for linear or whatever graphs, this would be good. But for these kind of graphs which have hyperbolic shapes, they don't really, if you have hyperbolic shape like this or something, a lot of the points aren't covered. And if you want to really truly demonstrate the verity of such an assumption, then I think you might want to consider that.
Yeah, it's definitely a nice suggestion from the opponent.
Okay, so let's talk about your theory. So could you mention again your reason behind omitting the z direction of equipotential lines?
For a reason that we think that for the scope of the experiment, we're considering that the equipotential lines are actually symmetric with respect to the plane, to the xy plane.
Yeah, I agree that they're symmetrical, but then I don't think that answers, I agree partly with their reason, but I don't think it provides the correct justification for that. I think it's because, so you have first of all, let's get this clear. This is your cap. Let's make it your cathode, and this is your anode, right, on the left. So then, does your cathode touch the bottom of the
No, it doesn't. It's very close to the bottom, but it isn't.
Yes. So you're going to have some direction over here that goes like this.
Yes.
then, if let's say your hyperbolic function is, let's say it's a metallic boundary condition, and then your hyperbolic function if you put the top would be something like this, right? But the problem is if you put your probe too deeply into this, there might be a difference in measurement in the z-axis. But I kind of agree with you. This is very, very minimal, so I think it is correct that you did it.
Since our detectors are electron objects, so there's a certain depth d, and we take it to be approximately less than 10
Okay.
so that's symmetric with respect to the main electron.
Okay, that's good. I would like to talk to you about boundary conditions. So what do you contain your water in?
It's a glass tank.
Okay, so glass is not really a conductor.
No.
So have you considered using a boundary condition, a Newman boundary condition of say metal or
No.
aluminum foil?
No, we do not.
Okay, I think that is unfortunately a pretty large overlook because let's say you have a metal plate, its electric field is going to be like this, and then its equipotential line is going to be perpendicular to its electric field. So when you have a boundary like this and outside is surrounded by metal, the equipotential lines, let's say you have your cathode on the left again, anode on the right again, it's going to be like this, slightly radiating outwards. And that is exactly what you found in your expectation slide. Oh yeah, it's right here. But the problem is you didn't mention the metallic boundary condition. You only mentioned that you had glass conditions, and that is very different. Because for glass conditions, you will notice that they will be shaped hyperbolically kind of like this.
There will be significant deviation from what we expect in this diagram. But according to our problem statement, it tells us to try to investigate how such potential lines may deviate from our expectations. So I think this is sufficient to show the possible deviation from what we may expect.
I must respectfully disagree because I think this is an important phenomenon that must be discussed because this is, of course, definitely another deviation that will occur. Changing the boundary conditions and changing of the electric field and the equipotential lines inside is definitely a very large phenomenon to be observed.
Yes. About this, I agree with you.
So, stern layers. So I'm glad you talked about stern layers. So, just to make sure we're on the same page, when you have another tank like this, let's say this is the cathode, so it's positive, and I have stuff here. They're going to create their own electric field here, right?
Yes.
So that will cause a stern layer, and this is a diffusion layer.
Yeah.
That will increase the overall electric field over there. Okay. And next, can you show me your hyperbolic? Sorry, your Boltzmann-Poisson equation, please. Right. So, okay, I saw a sign H. Could you move to the next slide? Yeah. So we did consider using hyperbolic sign to model it, and I'm completely unclear as to why you didn't end up using that because a lot of Python programs can't handle such things. So if you have if you can't shrink down the whole thing into a hyperbolic sign graph, it's unable to handle such variables. So, in fact, what's the approximate voltage range you use for your experiments?
It's under 5 volts. Here we can see the maximum is about 5 volts, and the minimum after which we can measure the voltage is about 5.
Okay, so first of all, that's probably not a very safe voltage to use. But other than that, I think a lot of such Python programs and graphs, they can't handle anything larger than 10 to the minus. It's very small, so much larger than this. And this also connects to your other point about concentration. So you concluded that concentration does have an effect.
Yes, it's a quite significant effect on the observed.
Right, so how many experiments do you do for this? Because I don't see any error analysis or error bars.
Yeah, we're indeed lacking in some data points. Yeah.
So how many experiments? I know you're lacking, but how much?
Three for each of these graphs.
Okay.
And we take the average after we do all the measurements.
So
needed for the
you
graph.
only did 3 graphs, and that's all right. So now let's talk about the time of measurement, because let's say initially, first, did you investigate different materials you can put? Did you only investigate this using water, or did you put other, did you add NaCl, ZnSO4?
Yes. In this graph, you can see that we experimented with ethanol, with different concentrations of ethanol, and also we added in NaCl into a solution.
So that's good. So let's say we have a graph. This is position. So let's say position X, and this is let's say concentration. So initially, when you put NaCl in without the electrodes, the concentration is going to be the same throughout, right?
Yes.
Because it's equally distributed. But the thing is, after you insert the electrodes, the Na, let's say the plus and the minus, this is the anode and this is the cathode, and this is going to start moving this direction. And this is going to start moving this direction.
And after a certain time period, it's going to reach some sort of equilibrium, as shown in the graph.
Yes, it will show. It will reach some kind of equilibrium, but there is a time. So there is continuous movement, right? So if you draw time versus, if this is time and this is concentration, the concentration over here will probably go something like this, right? But the thing is, if you draw time versus that, then you're going to have, initially it's going to have a dramatic decrease, and then it's going to be stable, and then it's going to start decreasing again. The thing with these decreasing and increasing parts on the other side is that when you're decreasing, there are ions flowing through that are unequal to each other. So that will create a lot of confounding variables that will affect your measurement. But we've actually found out that from around the period of 5 to 10 minutes after you insert your electrodes in your water, depending obviously on the relevant parameters, this portion of time is the most stable and doesn't include confounding variables. Have you thought of including this?
Although we did notice such phenomenon in our experiments, we did not try to quantify this phenomenon according to what you said.
So you did notice that there was a stable, and you didn't take advantage. It's all right. So finally, you have a anode here and a cathode here. And when, as we discussed earlier, there's going to be a stern layer that forms, right? There's also going to be another thing. There's going to be accumulation of these things on the anode.
Yes,
there's going to be
accumulation of the charges also contributes to the shielding effects.
And especially if you have some atom that is a gas at natural temperature, it might cause a depletion at the cathode, at the anode, which would cause an even greater decrease in the anode from the expected deviation.
Yes.
So did you observe such a result? Did you consider that this could contribute to your great deviations, apart from your boundary conditions?
We think that for the first scope of this experiment, the reactions you mentioned are actually, at least we did not observe any sort of phenomenon.
Time is up.
So I will summarize the discussion. So thank you, Mr. Reporter, for a fruitful discussion. We discussed many important things, like how you could vary. You could first fix one voltmeter at one point and vary the other one to fit the expected shape of your hyperbolic function, if you had any, to find possible deviations. For theory, we discussed extensively boundary conditions, which would drastically change the shape of your equipotential lines due to electric field shapes. Also, we discussed stern layers and why a hyperbolic function would be a better model to use for a program that can handle such processes. We talked about some error analysis and how it was lacking data points, but we did come to a consensus together that there was a specific time interval depending on relevant parameters. Oftentimes in such experiments, it occurs within 5 to 10 minutes that it was best to conduct experiments. The reporter unfortunately didn't use that time, but we did come to a conclusion. Thank you.
So thank you for the reporter and the opponent. So for my question, please give me short answers in one sentence, or yes or no. So first is for the reporter. Can you tell me the reason why temperature affects the time and the less changes in the voltage, like you just said? One sentence, please.
Regarding the temperature effects, I think it's actually due to the rate at which.
Okay, thank you. So for my next question is, can you explain the equation on page 14 in one sentence?
This is a relationship between the various parameters, such as ion concentration, voltage.
This is your conclusion for all of your theory?
Yes.
Okay, so for my next question is for the opponent. You did mention about the angle of the anode and cathode. Can you predict the effect in one sentence?
Excuse me, could you repeat?
Do you think what's the effect of the angle of the anode and cathode?
They would change the magnetic field.
It will change the magnetic field. Okay. So for my next question is for both of you. Why do you think the threshold voltage appears?
Sorry, can you repeat the question?
Why do you think the threshold voltage appears?
I can answer that question. So I think the threshold voltage will occur because there needs to be a threshold voltage for the redox reactions to occur at the cathode and the anode. And for those reactions, they will give the Stern layers, which are really important to the deviation.
According to this,
One sentence, please.
okay. So according to our model, there needs to be a sufficient voltage at, and when it's under that sufficient voltage, the diffusion layer and the bulk layer can actually shield the voltage supply by the electrons.
Okay, thank you. And the next question is still for both of you. Can you give me the reason why it's not symmetrical when it's close to the anode and cathode? Just one sentence, please.
It's actually because of the distribution of the various parameters such as the concentration and.
Okay.
Wait, could you repeat your question?
The reason why it's not symmetrical when it's close to the anode and cathode.
Symmetrical with respect to what?
The voltage.
No, in what axis?
The center.
Okay, for my next question is for the opponent. So will increasing the data points that you just mentioned about improve the experiment? Why?
Of course, because improving the number of experiments will reduce the error in. And if he had error bars, they would reduce, and you could.
Okay,
find
so
more
and you
qualitative
also
answers.
mentioned that D dimension is necessary. You think is that correct?
No, I mentioned that due to a different reason than the reporter mentioned, the Z direction is not.
I think that there's an image chart that you can consider in that point. Thank you. there's a problem. So I'm going to review the problem number 8. So for the report, we see the problem statement, and the main focus is the potential lines under liquids and the deviation between expectation and results. So for the report, I do a summary. While his modeling have met plot lib, numpy, and Gaussian circles, and the EPL which we just we think that he said that the shareholder voltage appears. And the experiment is that he used Arduino, variable resistor, DC power, and some variables he used in his report. Then is for the report's pros and cons. He gave comparison to expectation of this experiment, gave extra variable like ion concentration in order to explain the difference between each experiment. He had fruitful with the report and explained the use of setups such as voltmeter. For the cons, he only considered potential lines on the XY plane which know the dimension, like the opponents just said. The setup is not labeled clearly, did not explain the non-symmetrical anode cathode potential distribution. He skipped some equations too fast, which we cannot clear enough to see the effects. Opponents, pros and cons. He pointed out boundary condition which we agreed that should be considered. He gave extra advice to the reporters at using different boundaries, discussed various things, but he did not discuss about the non-symmetrical potential line distribution at anodes and cathodes, and his discussion at blackboard was not clear, which we cannot easily clarify. So for this first clash, we see that the reporter said use fixed points in order to measure unstable sectors, but the opponent said that moving the voltmeter has hyperbolic function could not only use dot to measure, but should be more continuous. We agree with the opponent that we should move the voltmeter to get a better result. The next one is the boundary condition. The reporter said that he didn't consider this, but they agree with the opponent. And we agree, of course, we agree with the opponent because using a metal as a boundary might be a better idea. However, if the reporter was able to give the explanation of deviation, it will not be necessary. And for the next discussion is the time measurement. The reporter said they did notice that, but did not take into account. And the opponent said there should be a period of time that the equipotential line will be most stable. And we think that the whole process of the experiment should be viewed, like they might can record it or something else. Here are some points missed. Like there's not enough discussion about the non-symmetrical of the anode and cathode potential distribution, which I asked in my short questions, which I think if considering that they might can have an agreement on why there's this phenomenon or observation, or is there any relationship between the angles of the anodes and cathode affect this. And then they didn't consider, as the opponent said, he did not consider the 3D geometrical of the electrode, but they did not have an agreement on that. And we think that there might be an image charge of that since his anode and cathode is not just a point, but a long stick. Then different points on that stick can be, there can be many dots which the Z dimension can create multiple image charges which will affect his voltage line for his result, like in our imagination. Then that's the end of my report. Thank you for listening.
Okay, so I'll make a concluding remark. So first, as the opponent pointed out, the Z-dimension and potential line to be taken into consideration. Since we leveled all of our pins, as I said on the blackboard, the effect should be minimal. And we will consider moving the voltmeter for better results in future experiments. Also, we agreed that the boundary condition is very important for this experiment, such as the Neumann metallic boundary condition, and it may affect the phenomenon. Also, the electric double layers are significant in the measuring of the equipotential line, as mentioned in my presentation. And we do think that with our programming ability, we can analyze the result of the voltage we used. Also, we did not observe significant phenomenon regarding the significant depletion of concentration due to redox reactions or the depletion of the gas molecules. And yes, that's how I agree.
Any questions on third?
If you change the ion concentration for your solution, the equipotential line is symmetry or not, and why? Find reporter.
No, it's not going to be symmetric.
Do you think it's symmetric?
No.
No, and why?
I think it has to do with the distribution of the ions as said before, but the details we cannot be 100% sure.
Okay.
I must disagree with the reporter over here because I think even though there were, changing the concentration will not change the symmetry of the equipotential lines, because even if you have, say, Na and Cl as your change, increasing in Na on one side will also increase Cl on the other side by the same amount. So the equipotential lines will also be still symmetric.
We agree with the opponent, and like we just discussed, that we already saw the non-symmetrical on the side when it's close to them. But even increasing concentration, it will not make it more symmetrical. It will not have an effect on the things he did. The result.
Sorry, can I point out something? I previously mentioned that what I mean was not that it's going to improve its symmetry. I was saying that it's going to retain its symmetry, but the exact distribution of the equipotential lines may change.
I have a question for all of you. Do you think the electrode shape how to affect this experiment?
Can I go first? Can I go first? I would like to answer it first.
Yes.
So like I just said that if our anode and cathode is a dot, then it's simply is really ideal. So we can just use his theory to predict the result. But like if you have a long his anode and cathode can be a dot, so there will be a d dimension or the y dimension. So as we imagine, there will be that can be considered as many dots of the anode and cathode. So then it will have a z-dimension effect, and there will also be image charges. Like you will have when you have an electrode here, there will be an electrode on the other side. So we think that do affects the result.
What is your point?
I agree with the reviewer on all of the points he mentioned, plus the fact that when you have an electrode that is especially longer, it won't have the same magnetic field going around it as one that is especially small. But then again, as you mentioned earlier, a small one, long one is basically composed of many small ones.
I also have something, and I agree with both of your points, and also I'm going to add that the specific geometry of the electrodes is going to affect how the stone layers or how the layers of charged ions distribute on the near surface of the electrode. So yes, it's definitely going to affect what we measure.
Any other question? Inaugurating time. For reporter, 8, 7, 7, 7, 5. For opponent, 7, 8, 8, 7, 7. For reviewer, 8, 8, 8, 8, 7. Any comments? If no, let's ending this round.